Okay, today we're going to be talking about vectors, and I want to start off by talking about the difference between a vector and a scalar. A scalar is a quantity that can be defined as simply a magnitude but has no specific direction. So for instance, things like area doesn't have a direction that it's going, it's just a value, it's just magnitude. Or maybe volume or temperature. When you take somebody's temperature, you don't say that it has a certain direction. It's not going up, down. It's just, or east or west for that matter. It's just a certain value. Somebody's height, same thing. But vectors are quantities that have both magnitude and a specific direction. So for instance, velocity. Velocity has a certain magnitude, let's say 30 miles per hour, but you're going right or left, east or west. Force. You have something that's pressing down or pulling down or pushing up with a certain amount of magnitude. So that would be an example of a vector, or maybe acceleration. So these are things that have both magnitude and direction. So you may want to write that down. It has magnitude and it has a specific direction. Now let's talk about, for just a moment, how to distinguish between a point. So let's say we have a point here, and that point is A, B. That means from the origin, you're going over some distance A and up some distance B. Now the difference with a vector is you still have a point, but now you have an arrow that is going from the origin to that point. And so it has a component, let's just say it has an x component, so it would be this distance, and then it has a y component. So we use these brackets to denote a vector and distinguish it from a ordered pair. So ordered pairs have parentheses, and now vectors have these little brackets or braces, and essentially this is A and this is B, and the magnitude of that vector is the length of the arrow, and that would be, you could get that by Pythagorean Theorem, which we'll talk about in just a moment. And so normally when you have an arrow on the end of a line, you're used to that, meaning that the arrow goes on forever and ever. However, in this case, the arrow just simply tells you which direction that this object is going, or which direction the vector is pointing. And so, but it stops at a very specific point, which gives it a magnitude. Now, something important for us to understand, and that is that vectors can also begin at points other than the origin. And here's the important part. However, any two arrows with the same length and pointing in the same direction represent the same vector. So you could have a vector that looks like that. You could have another vector over here that looks like that. You could have another vector here that looks like that. Another vector here looks like that. And guess what? If they're all pointing in the same direction, meaning they have the same slope and they have the same magnitude or length, they are the same vector. And to determine whether two arrows have the same vector, we're going to use what's called the head minus tail rule, which we'll talk about next. Okay, the head minus tail rule basically is a rule that enables us to determine whether two arrows are the same vector. And so it says that if you have an arrow that has an initial point of x1, y1, and we will call that the tail. So we'll call that the tail. And that is essentially where the arrow starts. And then we have another point that it ends at, and we'll call that the head. So you have 2 points, and the arrow goes from one point to another point. You can express the vector with these brackets, and it'll be the head minus tail. So it'll be the x-coordinate of the head minus the x-coordinate of the tail, comma, y-coordinate of the head minus the y-coordinate of the tail. So let's just jump in here. Example 1, show that the arrow from R equals -4, 2 to S, -1, S is the same vector as the point P, which goes for the arrow that goes from 2, -1 to 5, 3. So we'll do RS first. So we will go left 4. So 1, 2, 3, 4, and up 2. So this is the point R. And this is going to go to -1, 6. So 3, 4, 5, 6. And that is S. So it goes from R to S with an arrow, and it stops at S. So once again, R is your tail, and S is your head. So let's go ahead and subtract it. So the vector RS, which we'll express this way, RS with a vector, is equal to this bracket, and x2 minus x1, so it'll be -1 minus a -4. So -1 minus a -4, comma, and then 6 minus 2, bracket. So vector RS can be expressed as a minus is a plus, so it's going to be 3 and 4. Now, there's a nice easy way to do that. If you go from where the vector starts and you say, how far over do I have to go? Well, I've got to go over 1, 2, 3. How far up do I have to go? Up 1, 2, 3, 4. There are the components. And by the way, these are called the components. This is called component form. So when we ask you for the component form, we're simply asking you for the x and the y components of this vector. So this vector is the hypotenuse, it is the magnitude, and the components are the other two sides that make up the triangle. So nothing new in this video really about vectors. So let's see if we can now express vector PQ. So vector P goes, PQ goes from 2, -1. So we're going to go right 2 and down 1. And we're going to put a point. We'll call that P. And then Q is over 5. So 3, 4, 5, and up 3. And so now we're going to draw an arrow. We'll call that point Q. And let's do vector PQ. That's going to equal the head minus tail. So it's going to be the x-coordinate of Q, which is 5, minus the x-coordinate of P, which is 2, comma, the y-coordinate of Q, which is 3, minus the y-coordinate of P, which is -1. So we get a vector PQ, which is equal to 3, 4, and because vector PQ has the same exact components as vector RS, we can say that vector RS is equal to vector PQ. Why? Because they are pointing in the same direction and they have the same magnitude. Okay, let's talk real quick about how to find the magnitude of a vector. The magnitude of a vector is simply the distance of the vector. You could think of it as the hypotenuse of the right triangle. That's probably the best way to think about it. So let's just jump right in. It says here, to find the magnitude, you basically use the distance formula, but you know what? That is too difficult to remember. So we're going to use something that we've already known how to do, which is a Pythagorean theorem. So we have point P, -3, 4. So that's going to go 1, 2, 3, and up 4. 1, 2, 3, 4. And that is my point P. And Q is -5, 2. So it's going to be -4, -5, and then up 2. And that's going to be my Q. And so this arrow goes from P to Q. And so now if we were to make a little triangle, we could see that, okay, this distance of the triangle looks like it is 2, because you're going from -3 to -5, so that's 2. And then this is a height of, it looks like 2 as well. So that's going to be 2. And so to get the magnitude, you just simply do the Pythagorean theorem. So it's going to be 2 squared plus 2 squared is equal to, and we'll call this, we use these absolute value bars to represent the magnitude. So it's going to be 4 plus 4 is 8. So the square root of 8, because you have to take this, it's a squared plus b squared equals c squared. So PQ, the magnitude or the length of that vector, is going to be the square root of 8, or 2 root 2. Now, let's also talk about the components again. Let's continue to review. The components, once again, now you have to go from P to Q. So now this is where direction comes in. You got to be very careful. From P, you're going left 2 and down 2 to get to Q. So the components, you have to be careful. You have to actually pay attention to which direction you're going. So you're going left 2 and down 2, which means that another equal vector could be a vector that's coming from the origin that is going to the point -2, -2. So this is the point. Here is the point that's going, here's the vector that's coming from the origin to that point. These two are equal vectors because they have the same magnitude and they're going in the same direction. Okay, now let's talk about certain operations that you can do with vectors. You can actually add vectors together and you get an entirely new vector. And you can also multiply an existing vector by a constant, as is the case in letter B, which is going to make that vector smaller, or should I say longer or shorter. And so let's go ahead and look at this first one. You have vector u plus vector v. So simply, if we figure out what u plus v is, so we'll say u plus v is equal to, and all you do is the simplest thing. You just add the x's together. -1 plus 4 is 3. And 3 plus 7, you add the y's together and you get 10. So u plus v is vector 3, 10. So let's just kind of show you a little bit what this looks like. We'll use blue for vector u. Vector u has brackets -1, 3. Now, all vectors will be drawn from the origin to this point. So -1, 3 is going to be left 1 and up 3. And so there is vector u. And then we will use green for vector v. Vector v is going to be over 4 and up 7. So that's going to be 3, 4, 5, 6, 7. And so here is vector v. From the origin, goes to that point. You add these two together and you get a totally new vector, which we'll use red for, which is over 3 and up 10. So that's right about there. And this is the resulting vector. It's called the resultant vector that you get when you add the blue vector, which is u, with the green vector, which is v. You get a totally new vector there. All right, letter B, 3 times u. Well, we see that u is once again -1, 3, so that's going to be left 1 and up 3. So there is vector u. Now if we take vector u and multiply it times 3, we get a new vector, which is 3u. And all you do is simply multiply the x component by 3, which is going to be -3, and the y component by 3 as well. It's going to be 9. And so now we are going to use green for that one. So now you're going to be going left 3 and up 9. So that's going to be up here. So now you have a vector that is 3 times as long as vector u. Okay, letter C. You have 2u plus -1v. We're not going to try to sketch this, but we will say 2 times u. So let's just write this out. 2 and then times u plus -1 times v. So we're going to multiply the u vector by 2, and we get negative 2, 6. And plus, we're going to multiply the v vector by negative 1. We get negative 4, negative 7. Simple addition. So now we're going to add the x components together, and you get negative 6. And then you're going to add the y's together. You get negative 1. And that would be the components of this new vector. And just to review, if you wanted to get the magnitude or the length, you would do a simple Pythagorean theorem. So you'd have negative 6 squared plus negative 1 squared, which is 36 plus 1. Root 37 would be the magnitude of the vector if they asked. So I'm just trying to review and cover those concepts as well. Okay, next we're going to talk about what's called a unit vector. And a unit vector is simply a vector that has a length of 1. That is important. So very simple. It has a unit vector is a vector that has a length of 1. The hypotenuse, the magnitude, is equal to 1. So this first example says find a unit vector in the direction of negative 3, 2, and verify that it has a length of 1. So if we draw a little xy axis and we put the point negative 3, 2, let's draw that vector. So it will be left 3 and up 2. So 1, 2, 3, and up 2. So left 3, up 2, and there is the vector v, negative 3, 2. Now, clearly, this does not have a length of 1, because if we were to get the magnitude of this, well, this is a length, we'll just put negative 3, but we're going to square that, so it doesn't matter. So if you do the Pythagorean theorem very quickly, you'll get 3 squared, which is 9, and 2 squared, which is 4. So the length of this vector is root 13. That is not a length of 1. That's much bigger than 1. So what we want to find is a new vector that is going in the same direction but has a length of 1 and not root 13. So all you do is you take the components of this vector, so negative 3 and 2, and all you do is you divide them by the magnitude. Divide them by the magnitude. You may say, well, why would you do that? Well, let's just think about it. If you take this green vector that I drew at the beginning and you divide that magnitude by root 13, what's root 13 over root 13? That's 1. But if you're going to scale down the hypotenuse of this triangle, you must also scale down the components of this triangle as well. And that way you will get a much smaller triangle with a magnitude or hypotenuse of only 1. So these are the components of your unit vector. And then it says verify that it has a length of 1. So what we're going to do is we're going to do the Pythagorean theorem. So let's prove this. Negative 3 over root 13 squared plus 2 over root 13 squared. That should equal 1 squared. Well, let's see. Negative 3 squared is 9. Root 13 squared gets rid of the root, so that's going to be 13. Plus 2 squared is 4. Root 13 squared, once again, when you square a square root, it gets rid of the square root, and that leaves you with 13. So 9 plus 4 is 13 over 13, which is 1, and the square root of that is 1. So how do you find a unit vector? First of all, what is a unit vector? A unit vector is a special vector that has a magnitude, a hypotenuse, a length of 1. How do you get it? You draw the normal vector, you find the magnitude of that, and then you divide the components of that vector by the magnitude to scale everything down so that it has a length of 1. Okay, let's talk about what's called resolving a vector, which basically means you want to find the x and y components of a vector if we are giving you the angle that it goes in. So here's theta, And let's say we have this red vector. We'll call that vector v. It has a length or a magnitude or hypotenuse of a length v. And we have these components. We have the x, which is the horizontal distance, and y, which is the vertical distance. And these two make up the components of the vector. So let's say we're trying to find x, we're trying to find y. Well, this is good news for you because this is all stuff that you have done before. We have a right triangle, and so we're going to use SOHCAHTOA. So we will say cosine of theta is equal to adjacent, which is the x, over your hypotenuse, which is v. And so if we multiply both sides by v, the v is going to cancel. And so now we have x, which equals whatever the hypotenuse is, v, cosine of theta. Let's do the same thing for the y component. So we will say sine of theta equals opposite, which is y, over hypotenuse, which is v, multiplied by v, and now you get y equals v sine of theta. So now, from now on, you do not need to go through this process of SOHCAHTOA anymore. You can jump straight to this. And put that in a box for you. From now on, you can say, okay, anytime I am looking for the x and y components of a vector, and I have the magnitude of the vector, I've got the hypotenuse, I've got the length, and I've got the angle, I can just go and do v cosine theta, v sine theta. Don't need to go through this process anymore. So for example 5, very easy and quick problem. It says find the components of the vector v with the direction angle 115 degrees and magnitude of 6. So you've got the magnitude and you've got the angle. So this is very simple. 6 cosine of 115 and 6 sine of 115. And I know what you're thinking. Is that it? Yes, that's it. That's all you have to do. If you want to get a decimal equivalent, you can type that in your calculator and you can get the decimal equivalent. Matter of fact, let's go ahead and do that real quick. If we type that in our calculator, we get the vector v equals negative 2.54. Make sure your calculator is in degrees. And 5.44. That makes sense because if we have this vector and it is going in the direction of 115 degrees, we know that that is in the second quadrant. That's somewhere over here. And it makes sense that you would have to go left, which is negative, and up, which is positive for your y. Okay, in example 6, we want to find the magnitude and the direction angle of each vector. Once again, good news for you. This is something you've done lots of times over the last month or so. So we have the vector 3, 2. So that means from the origin, we need to go right 3 units and up 2 units. And so we're going to go from here to here. And so that is our vector. So it has components of 3 and 2. We do the Pythagorean Theorem. That's the easy part. 3 squared is 9. 2 squared is 4. 4 plus 9 is 13. So root 13 is the magnitude. So we'll say absolute value of u is root 13. Now we need to find the angle. Well, this is something, once again, we've done many times. We're going to use inverse tangent or inverse sine. Now, I highly recommend, and I'm going to put this down here, that you use, I'm just going to keep it simple. Let's all use inverse tangent to find the angles. That's the first thing. Second thing, you can disregard any negative numbers for as far as the components are concerned. We'll get into that in part B, and you'll see why in just a moment. So we're going to say theta is equal to the inverse tangent of opposite over adjacent. Let me explain why we want to use the inverse tangent. Because inverse tangent is going to guarantee that we get an acute angle, because inverse tangent only gives angles back in quadrants 1 and 4. Same with inverse sine. So we want an acute angle. You'll see why in just a moment. So inverse tangent of 2 over 3, theta is going to be approximately 33.69 degrees. So there's your direction angle, there's your magnitude. Part B, -2, -5. So we're going to go left 2 and down 5. And there is our point. So our vector is going to be drawn from the origin to that point. And so we have components -2, -5. And so we can do the Pythagorean Theorem. 5 squared is 25, 2 squared is 4, square root of that is 29. So vector V is square root of 29. Notice I did not use the negatives because when you square a negative, you're going to get a positive anyway. So I'm not squaring the negatives. I'm not using the negatives. And so we have this root 29. Now, theta, we'll use that as theta. And so we're going to say theta is equal to the inverse tangent of the opposite, which is -5, over, and I tell you what, I'm not going to use the -5. I'm just going to use 5 and 2. And we get a value for theta to be 68.19. But do not write that as your answer down. Please don't write that as your answer down, because 68 degrees is somewhere in the first quadrant over here. We're in the third quadrant. So 68 is simply this angle right here. It's the acute angle in the triangle. We've got to add 180 plus this angle, and that's going to give us the real angle of theta, which is 248.19. So you must add 180 to whatever acute angle you get, or if you're in the fourth quadrant, you have to subtract that acute angle from 360 to get the angle. Jump in this last example very quickly. We have an aircraft that is flying on a bearing of 65. Now we remember that bearing means you're measuring from the north and you're rotating clockwise. So that means you will be going from here and measuring 65 degrees in that direction. So that means that the plane is flying in this direction right there. And so we'll put a little tail on that. And so that means that this angle is 65, which means that this angle here is 25 degrees. And the magnitude or the speed of the plane is 500 miles per hour. So we'll put that as 500. And it wants you to find the components. So once again, we have done this earlier. So the component form of any vector is going to be the velocity cosine theta, the velocity sine theta. So it's going to be 500 cosine of 25. Now, I want to caution you. For this unit, you are going to have to be able to convert bearing into a real angle. Do not use 65, because 65 is not the real angle measured from the x-axis. It's not the unit circle angle. So you must convert all bearings to a real angle. So it's 500 cosine of 25, 500 sine of 25. We went over that earlier when we talked about v cosine theta, v sine theta gives you the components. And so the components of this vector is going to be 453.15 and 211.31. What does that represent in real life? Well, it represents the speed of the plane in the horizontal direction and the speed of the plane in the vertical direction.